So this afternoon, David is going to speak to us on cameras for deep space missions.
Thank you. Good afternoon. Having just seen the wonderful pictures we've seen of Jupiter's icy moons, I make no apology for the fact that I won't be showing you lots of fancy pictures of other planets. Although I started life as a physicist, I'm very much an engineer now. We deal in hardware, although it's useful for us to understand the science that our instrumentation is used for. Fundamentally, we make stuff and sell it to people. I hope what I'm going to show you today is not too much of a sales pitch. We are a commercial organisation based 2 miles down the road. If you want to buy something, see me later. But I'd like to give you a view of the sort of things that we have to do and we have been involved in supplying imaging detectors and subsystems into many of the missions that have been to the other planets in our solar system, and also have investigated the potential for planets in other solar systems. But first, of course, there is the planet we're on. And this is one of the few fancy pictures I'm going to show you. This is from some imaging sensors we supplied to the European Space Agency for the Sentinel-2 mission. This is our planet. So this is the recently launched Sentinel-2 showing an algal bloom in the sea. And you can just see a ship sailing across it. So, very briefly about us. I have to give this bit first if I'm representing the company. The E2V group, as I say, is based in Chelmsford, 2 miles down the road in Waterhouse Lane. We have 11 global locations, of which 4 are production facilities. We serve the whole world. 50 plus countries means everybody that's got money. We were founded in 1947, making magnetrons. We have about 1,700 people, of which around about 1,000 are in Chelmsford. A significant proportion are trained engineers and scientists. We also have facilities around the rest of Europe, in the USA and in Asia. We are divided into 3 sections, of which only one is interesting, obviously. The RF power generation is our history, doing exactly what it says. It's radio frequency power for a wide variety of things, from Linac magnetrons for cancer therapy to radar to industrial heating. We also make high reliability semiconductors for airborne aerospace applications, for a wide variety of high-speed communications applications. And in the center we have what we call high-performance imaging, which is fundamentally imaging sensors, mainly in silicon, focal plane arrays, cameras and subsystems. And within that now divides into 2 sections, and I made the one on the right look bigger than the one on the left. So we have a professional imaging organization which does fascinating things like barcode readers and inspection cameras, intraoral dental things. We are not professional imaging. We are the gifted amateurs who do space imaging, ground-based astronomy and other high-energy physics type applications. So within space imaging, we serve pretty much all sectors there are for imaging in space. Space science generally gives us our biggest opportunities. Space science spends money in large lumps on detectors. They're good lads, the space scientists, because they understand that the detector makes the system. Earth observation, which tends to be much broader based into a wide variety of different customers across the world. Ground-based astronomy, which we consider to be space because that's what it's actually looking at, where we supply, again, large focal planes, very customized detectors for almost all of the world's large telescopes, be they survey telescopes or spectrometers. And some activity in high-energy physics experiments who also have a similar sort of need for detectors which perform very well in very specific circumstances. Where we've been and where we're going, in terms of planetary exploration, and I've rather cheekily included the sun as a planet, which obviously it isn't in this case, but looking out through the solar system, we've been to Venus with 2 or 3 missions, Venus Express with ESA, Akatsuki with JAXA. Akatsuki wasn't a spectacular success. Its first try, it missed Venus, but second go, it's actually managed to get there this time. We have a significant number of missions to Mars that we've been involved in. Currently, we have several detectors for doing a variety of experiments wandering around the surface of Mars on the Curiosity rover. In particular, something called ChemIn and ChemCam, which are looking at the composition of the Martian surface. We have what has been actually a very spectacular imaging mission, which is on the Mars Reconnaissance Observer with NASA, an instrument called HiRISE, which has taken a vast amount of data mapping the surface of Mars. We have been involved with ESA on ExoMars. ExoMars has, I guess you probably realize, has two launches. The first one has just gone. The next one is due to go in a couple of years. Where we've had involvement with the Open University in something called NOMAD, and subsequently 2 more instruments to go onto ExoMars lander in a couple of years' time. We've been going to Mars for a long time. We were first involved with Mars 94, and our involvement with that would have been 10 years before that. Part of the benefit we have, which we'll see more in the case of something like Rosetta, as Mark would have spoke about earlier, and even more the case with New Horizons. We have the benefit of being involved as a manufacturer of bits. We have the benefit of being involved relatively early in a mission. So there will be a phase of a space mission which says, what should we do? And we're having decided that, exactly as Geraint was saying earlier, there will be some evolution of the mission requirement. Generally we'll be involved in that sort of part of the mission definition. When it finally gets defined to the extent that our customers decide to buy something, we will be designing, manufacturing and delivering the sort of devices they need for their instruments. And then for us, effectively, the job is over. And so JUICE will be a good example in that we will deliver what we need to deliver for JUICE probably in a year's time or so. And then it's over. And then in 14 or 13 years' time from then, everyone gets excited because it's got there. And we get publicity from the wonderful pictures that come back for 13 years' time. So we have to make the most of that. So I have my New Horizons shirt on here. New Horizons, of course, has just last year has done its flypast of Pluto. Our involvement in New Horizons was 15 years ago. So fortunately, I'm old enough to have been involved in New Horizons. But many of the people at the factory now say, well, that's fantastic what we've achieved, but of course it was achieved 15 years ago. So we have to make sure we make the most of that publicity when it arises. We have several missions to the moon. The next one again will be the next Chinese Chang'e mission to go up Chang'e 5. And a variety of Indian and ESA missions to the moon, looking both at the moon in terms of visible mapping, but more recently there's been activity looking more at the composition of the lunar surface from remote sensing instruments. More particularly with X-ray fluorescence with Chandrayaan and Smart 1. I won't dwell on JUICE because we've just had a fantastic talk about what JUICE is supposed to do. We do have instruments on Juno, which again we're just about to get some publicity for, we hope. We will be supplying the imaging sensors for Janus, which will be the high resolution imager going into JUICE. Working again with the Open University in that case, and also with DLR in Germany. Moving on, coming to the Sun. The Sun presents a little challenge from the ground to see what it's about. It's bright and it's there most of the day. The difficult bit about the Sun is understanding the internal dynamics, and to do that you need to look at the Sun in higher energy photons. So one of the benefits we have developed is the ability to operate our detectors in very short wavelengths, so down to a few nanometers. So the graph on the right effectively shows what ground-based astronomers would like to optimize for. So wavelength sensitivity from UV to near IR when they want the best possible quantum efficiency over this range. In practice, with modification to the material physics of the surface of the detector, we can extend that wavelength sensitivity right down to 1 nanometer relatively easily, which makes it possible to take these sorts of images. This is from the Solar Dynamics Observatory, for which we delivered detectors a decade ago now. SDO is a fabulous facility. Its cadence is high, and I believe it's just delivered about its 100 millionth image of the sun. And if you have the opportunity to look at their website, if you've done it already, will give images of the sun in a variety of wavelengths several times per day. So, and there is a massive archive of these images. So if you want to get a picture of the sun on your birthday, this is the way to go about it. I won't talk much about Rosetta, because I guess Mark has gone through his usual massive and very impressive discussion on what Rosetta is about, but I will talk about what our involvement was. For me, Rosetta started in the 1990s, working with the scientists at the Max Planck Institute in Katlenberg, Lindau, who had this mad scheme of putting together instrumentation for a mission like this. Over the subsequent 5 years, we worked with them to develop and deliver the detectors for the wide angle and narrow angle cameras for OSIRIS on Rosetta, and subsequently the imaging system for the navigation camera. So on the orbiter, the navigation camera uses a relatively prosaic, what we call our CCD 4720. This detector on the left here on the nav cam probably has been in space as a detector more times than any other. Conservatively, design will have flown on a couple of hundred space missions. And it's done a wide variety of science, from navigating things like this to being in star trackers in many missions, to being used for satellite surveillance and tracking, to going to Venus, to looking at ultraviolet surfaces of the moon, to a wide variety of other things. It's a workhorse device, and has been probably to more planets than the other detector as well. The OSIRIS detectors, both detectors in the wide and narrow angle cameras in OSIRIS for Rosetta are the same. Were developed between ourselves and the Max Planck Institute. What you're seeing here is actually it's in its transportation container. So the grey metallic part is the transportation part. The detector surface itself is the blue-grey part on the top, and the electrical and mechanical interfaces are underneath. And the top right is the detector that goes into the Vertis instrument. On the lander itself, we supplied two imaging systems, both using the same detector, SIVA, and also into ROLIS, the Rosetta landing imaging system. All of these things, despite their long hibernation, functioned extremely well in Rosetta. So, one of the nice things about the space environment, with the exception of, again, what Geraint spoke about earlier, is that once you've got there, it's relatively benign. So although the rigors of launch can be quite unpleasant for complex hardware systems, once you get to space, as long as you've done the design right, the thermal environment is relatively stable. There isn't much vibration. There's not a lot of thermal cycling in most cases. It doesn't get shocked very much. The only thing you have to worry about is it's in vacuum. That's a design issue. And secondly, you have a somewhat unknown radiation environment, and that probably is the biggest risk that our subsystems and detectors run in all of these space missions, in particular in planetary space missions, not knowing particularly well what the radiation environment is going to be either on the way or when you get there. So we have to take a significant account of design of subsystems to take into account a worst case radiation environment. As I said earlier, New Horizons, our mission to Pluto, helped by NASA, in both cases with Rosetta and New Horizons, obviously huge teams of people involved in making it happen. I think the real heroes, and I think will probably be the heroes for JUICE as well, the real heroes are the flight dynamics people. Getting it there in the first place is really quite important. Having the hardware on it that does the job is nice, but if it doesn't get there, then it's not actually a lot of use. So for New Horizons, we supplied a very bespoke detector for what was called the Ralph instrument. Again, a long time ago. The science payload on New Horizons for us really was just the Ralph instrument, which is a high-resolution, quite bespoke time delay and integration sensor with multispectral capability, which was used extensively, particularly on the fly past, but also looking back at Pluto after the fly past. Also provided high-resolution colour images of Sharon. And the long-range reconnaissance imager, which actually gave both the direction for the spacecraft, but also gave the images of Pluto and its moon, or moons, I guess, if you can, as the spacecraft approached and as it receded from Pluto. New Horizons is now on its way to the Kuiper Belt. I'm not sure they've actually succeeded in finding a real target yet. They think they have, but it remains to be seen whether the flight dynamics people succeed this time. A couple of images here on the left. That's Jupiter, which New Horizons took a snap of as it flew past. And this on the right is the detector that took the image and took the previous image, in fact, with the colour images of Pluto itself. We developed this with our customer at the time, was Ball Aerospace in Boulder, in Colorado, which is a relatively complex detector with 6 colour charge coupled device time delay integration sensors, so it relies upon the motion of the spacecraft to generate the image. And coincidentally, I had a discussion yesterday with another team from NASA who are now proposing a new discovery mission, which will also go to the outer solar system, and they would like to have an updated version of this sensor. One of the other aspects of the sort of industry we're in supplying hardware into space missions is it's extremely conservative. So what NASA is now interested in doing is saying, can we have the same again, please, but slightly different? And you have to remind them, we designed this 20 years ago. In semiconductor industry, 20 years ago is prehistory. Fortunately, we can still do it, because we are, to an extent, prehistoric in our approach. So it is quite feasible for us to make an updated version of this sensor that went into the Ralph instrument. They take some convincing that it should cost more now than it did 20 years ago. But then in the end they pay their money and take their choice. How are we doing for time? The long-range imager, as I say, again uses the CCD47, which was also used for Rosetta. The advantage of this device is not only that it's relatively simple to operate, we now make it in a wide variety of different flavors for different spectral imaging. The conservative nature of the industry says, okay, so this has flown, and there are several hundred of these things flying. We probably won't take a risk on using something different next. We'll use that one again because it does perfectly well. So it's a workhorse. and does produce images like this of places like Pluto. Moving on to planets that are not around stars or our star, there are a couple of specific missions that have very different aspects than we've just seen on the sort of thing that are for planetary explorers who actually go to planets. The requirements of those missions are quite different from things that look for planets around other stars. This is the focal plane for NASA's Kepler mission. On that, you have a significant number, I think from memory it was 48, detectors that we built, again for Ball Aerospace in this case. And I see several of my colleagues over here who might have worked on that program. Kepler has been a great success, mainly because it was the first large observatory that was doing this sort of work. So it's looking for occultation of stars by planets. So it's measuring the changes in the output of the star as perceived with and without the planet in front of it. The catalogue now of planets that have been discovered by Kepler is over 1,700 and growing all the time. It did have a bit of a wobble, I mean literally had a bit of a wobble. Some of its stabilization system failed, but somebody very clever has worked out how to stabilize that without the system being in place such that you can still use Kepler for doing its original purpose. There was some talk about repurposing Kepler to something different because it was there, but it was worked out that it could continue its main function of discovering exoplanets. From our perspective, this was a great project. They wanted lots of detectors and were prepared to spend a reasonable amount of money doing it. But of course, the publicity of being able to discover new planets around other worlds is fantastic. The next one for this will be ESA's, or the next big one for this will be ESA's Plato mission, which has been selected and should be adopted in theory in November this year. I think it was going to be June, but they had a wobble as well. This, for us, will be our largest ever, we hope, will be our largest ever project. They will require 152, current design, 152 flight models of a detector, which is, you can't really get the scale from that picture there, but the detector is, each detector is about this big. It's a significant size. So they will be arranged as four detectors on a plate. Each of those 4 detectors will be a focal plane behind a telescope, and there will be 34 telescopes. It will form the largest focal plane area that has yet been launched into space. So we're looking forward very much with crossed fingers that ESA will complete its adoption of Plato at the end of this year, and it'll keep me employed probably close to when I need to retire, which will be quite handy. Slightly off topic, but when we say about the largest focal plane area to be flown, currently the largest focal plane area that's flying is ESA's Gaia mission. Gaia's main purpose, its first science requirement is about astrometry. It's about mapping the positions and proper motions of 1 billion stars in our galaxy. And it has 1 pixel for each, roughly. So it's about a billion pixel focal plane. This was built by Airbus in Toulouse, but we supplied 106 imaging sensors, and again very specialized imaging sensors, to them to build into this focal plane. It's due for its first science release. There have been some preliminary data releases which shows everything's great, and that the algorithms used to retrieve the data are operating, but the first science release is due in a few months. The mission itself is due to last a few more years once it gathers all of the data to get this proper model of our galaxy. But by the nature of what Gaia does, the secondary science is actually massive, so it will find a wide variety of other planetary bodies. It will find asteroids that we don't know about yet. It will find all sorts of other stuff, just because it's looking in huge detail at our galaxy. and the focal plane itself looks like this. The little grey bits, one of which is on the top left, is the sensor we've delivered, which are constructed into this complex focal plane, which is, say, currently flying at L2. Each of the devices having its own particular purpose. The field in the middle is the main astrometric field, but there's a radial velocity spectrometer at one end, which is designed to calculate the radial velocities of the stars in the galaxy. And the things on the far left, which is one is the basic angle between the two telescopes on Gaia, and the sky mapper, which determines which of the two telescopes each of the star signals that they get onto the focal plane has come from. This was our biggest project, or has been our biggest project to date, in terms of supplying detectors and money. Plato will be bigger, both in terms of the area and the number, and hopefully the money as well. And finally, we don't just do stuff for planetary exploration. We also do a large amount of work for astronomy itself. So simple focal planes for ground-based astronomy and space-based astronomy is our bread and butter. We have Gaia again at the top. But many of the world's large survey telescopes now require significant focal planes of high-performance detectors, and we have a list here, which I won't go through, of several of those. Supplying large focal planes of very high performance, very high quantum efficiency, very low noise detectors is very much our bread and butter. So over time, from Hubble, which was a long time ago now, to JPAS on the bottom right, we have assisted the astronomical community in gathering the data they need. The next big thing, the next big science goal is about understanding dark matter, where it is, what its distribution is. And there are several projects looking at this, which we're helping with, one of which is the Large Synoptic Survey Telescope based in the USA, which is now procuring, again, a very large focal plane of detectors. And these are very specific detectors with really quite demanding performance, not just in terms of the quantum efficiency, the wavelength range, the noise, but also its physical characteristics. It has to be very flat. It's a very fast telescope. They want a very large focal plane. The whole thing has to be very flat. So it's stressing our mechanical as well as our electro-optic capabilities to supply this. But it's working. Another allied project, or probably competing project, is what's called JPAS, which is a Spanish-Brazilian collaboration, again, to look at the distribution of dark matter in the universe, where, in this case, we've expanded our scope of supply significantly from just the detector at the top, and this is a bigger detector than I was talking about for Plato. This is this big. This is 9 centimeters on a side. Where now we're supplying the whole camera. So when I say camera, it's literally this size, which bolts onto the back of the large telescope. And the complexity of this system is difficult to overestimate. Not only does it have a large focal plane, there's a lot of electronic systems involved to drive and take the data from the focal plane, but it all has to be cooled to minus 100 degrees in vacuum and maintained like that for months. So it's nearly finished. So I won't go through the status in detail, running out of time, and I can see it's time for coffee very shortly. But this is in our clean room now. The integration is pretty much finished, due to be delivered in June. An exploded form looks like this. So within here you have a focal plane within a cryostat with all of the cooling required to operate this at minus 100, with all of the electronics bolted on the back to read out the data from all of the detectors, plus the vacuum requirements, so there are vacuum pumps. The cryostat itself has to hold the detectors and have a window on the front which has optical power, so the window is not flat. It forms effectively the last element of the optical system. It all has to be constructed such that it can operate not only like that, and that's an exploded view obviously, but such that as the telescope slews it maintains the performance and the flatness and the temperature of the whole system. And it has to be tested at our place and delivered to a mountain in Spain and still work when it gets there. So thank you for your attention.